In topology, a Clopen set in a topological space is a set which is both open and closed. That this is possible may seem counterintuitive, as the common meanings of open and closed are antonyms, but their mathematical definitions are not mutually exclusive. A set is closed if its complement is open, which leaves the possibility of an open set whose complement is itself also open, making both sets both open and closed, and therefore Clopen. Examples: in any topological space X, the empty set and the whole space X are both Clopen. Now consider the space X, which consists of the union of the two open intervals and of R. The topology on X is inherited as the subspace topology from the ordinary topology on the real line R. In X, the set is Clopen, as is the set. This is a quite typical example. Whenever a space is made up of a finite number of disjoint connected components in this way, the components will be Clopen. As a less trivial example, consider the space Q of all rational numbers with their ordinary topology, and the set A of all positive rational numbers whose square is bigger than 2. Using the fact that is not in Q, one can show quite easily that A is a Clopen subset of Q. Properties: a topological space X is connected if and only if the only Clopen sets are the empty set and X. A set is Clopen if and only if its boundary is empty. Any Clopen set is a union of connected components. If all connected components of X are open, then a set is Clopen in X if and only if it is a union of connected components. A topological space X is discrete if and only if all of its subsets are Clopen. Using the union and intersection as operations, the Clopen subsets of a given topological space X form a Boolean algebra. Every Boolean algebra can be obtained in this way from a suitable topological space. See Stone's representation theorem for Boolean algebras.